Graph off. Okay. This is where I wanted to start. Okay, this is where I want to start. So here is the rate of change graph. And so as time goes by, this is showing how that rate of change graph emerges, point by point by point. Okay? And so we have what? Constant rates of change every half second. And then abruptly changing to a higher constant rate of change. Right? So we think of this basketball having booster rockets. Every half second, another rocket goes off, and it suddenly jumps to a faster rate of change of height. Okay? So what over here then, this is also the number of seconds on our x-axis. Both of them are number of seconds since launch. And then the y-axis on our right graph is the focal quantity. In this case, that focal quantity is the height of the basketball. The height of the basketball. So now we want to actually graph this, what we call an accumulation function, or graph this height function as time in seconds goes by. So based on that rate of change graph, based on the rate of change graph that you have, can you think about and predict what the height function in this right-hand graph will look like when I turn it on? Okay, and so try to think of it as many specifics as you can in terms of what that height function will look like. Why don't you just take 30 seconds, discuss, talk with the person next to you. What will the height versus time graph look like, the accumulated height graph, based on that rate of change graph? Go. Okay, so I have a question. Is the graph curved? Is it a curve? Is it curved? It's a graph. Here's some no's. If it's not curved, then what is it? Okay, some people are saying it's a bunch of straight lines, right? If we have this piecewise constant rate like this, they're all constant rates. What kind of graph do we get? What's the name of that? You're Christian.
Piecewise function.
Yeah, so this is a piecewise, right? And each piece is a?
Function.
Each piece is what kind of graph? A curve? A line. Piecewise linear. So let's zoom in on that and see that for real. So I'm going to, if I zoom in, you can start to see it. Do you see that that's a bunch of straight lines? Okay, not oh, brother. Let's turn this off earlier here. I think it's this one. Yeah, good. Okay. So that's a bunch of straight lines, and you guys have practiced writing functions that have a graph like that, piecewise linear functions. So let's come over here and look. So where are we at here? Maybe we're at, let's roll it back a little bit so we can see better. So how about here at 3.41 seconds. Okay, so we're at 3.41 seconds. No, we're not. less. There we go. That's good. 2.85 seconds. So at 2.85 seconds, so what does this point on the graph represent? What does that point represent on this graph over here on the right? What does it represent? Yes, sir. He said the height of the ball in feet, which would be our y coordinate, at 2.85 seconds, the x coordinate. So again, it's two values, corresponding values taken together, a time and a height. Okay, and so this, if we were to graph this height function, or write the equation for it, what would it be? What would it look like? What would the rule for that height function look like? Just one little expression here, one equation? No, right? So it'd be a big, long thing, right? Like this. So for this point, there's some line that applies, right? Somewhere in the middle. I want you to write that line right now. Write that line that would apply to the current point, which is what? 2.85 and h of 2.85. If we're calling that yep, I'll write it on here. Remember that the rate changes every half second. So there are your values on your axes. Every half second, the rate changes. So what's the current rate of the basketball at 2.85 seconds? 5. So it's going to be 5 times x minus 2.5, starting value of time at in this interval. Then and that's from how'd you do? Get it? So the way that we're thinking about this is h of 2.5. That's all the accumulated height up to 2.5 seconds. And then we're adding on the accumulated height in this interval, or at this rate, at this current rate, which is 5 feet per second. So this is the amount of height gained in the current interval, or at the current rate of 5, plus all the height gained from before. Right? And so all the height gained from before would be this y value. See, so h of whatever h of 2.5 is. That's not the straightest line I've drawn today. You get the picture though. So that whatever that y value is at 2.5 is the height of 2.5, and then this other part is the change in height, right? The change in height. K delta x. K delta x, the change in y, or in this case the change in h. Okay, so that's one way to think of this output, but really you've been reading and we've been talking about accumulation. How do things accumulate? bit by bit. So this isn't really a bit. It's just a big chunk of change that we're starting with, and then we're adding the current change. So how can instead we think of this h of 2.85 as accumulating bit by bit by bit? So that's what this is showing here. So this y value at 2.8.5 can be thought of as velocity 1 times the first change in x, or 0.5, velocity 2. This is actually velocity 2. Velocity 1 is 0. So velocity 1 in the first half second is 0. So this is actually 2, and then 3. So this total h value at 2.5, you can think of it as delta h1 plus delta h2, and each of those delta h's can be computed by k delta x. In this case, k is velocity. So we saw that in your homework for today. A little bit of change plus a little bit of change plus a little bit of change totals up to the current value of the quantity. And each of those little bits of change can be, since we have constant rates, we can use constant rate of change to calculate each of those with little bits of change. K delta x plus k delta x plus k delta x. Anybody have a question? So now we're ready for this page, I think. Okay, so here is showing that same thing for 8 seconds. So this amount, this height of feet from the ground at 8 seconds, is the sum of all these little bits of change, each one computed by constant rate of change, because that's what we have.
So
Yeah, go ahead.
velocity 1, velocity 2, delta x. Since I think you just answered it.
Okay. Yeah, so here I've labeled the velocities. Okay, those are just like we've talked about k in the past. The rate of change here is velocity, so I'm saying v instead of k. And so then you think about all these little k delta x's, in this case v delta x's. All right, we're adding them all up. So the accumulated distance through the first 11 intervals, which would be 0 to 5.5 seconds, would be this sum right here. So this embodies accumulation, bit by bit by bit. It also is using constant rate of change for each bit. Okay? And we can use summation notation then to represent that. Okay, so this is all kind of review. Should feel like review. Okay, anybody have a question? For this example. Yeah.
As far as the notation goes,
Yeah.
What if your last delta x isn't the same? Like, what if you're at 5.2?
Oh, yeah, we're getting there. Yeah, you're just about a week ahead. Yeah, it's perfect. It's the right question. It's just not the right timing. Yeah. Yeah.
So what's h of what?
Okay, so that's good. I'm glad you brought that up. So we can think of h, as the name of the function. So the input into the function wouldn't be 11. What would the input into this function be? Okay, my colleagues are going to get me on this, but so the input of the function is 5.5 seconds. By using the subscript, we're referring to the number of intervals that we've gotten up to, okay? Just forget this. Just forget this. How about h of 5.5? Is that better? Let's just do that. So it's the sum of all the accumulation in the first 5.5 seconds. Because our delta x's are half a second, then it's going to take 11 intervals to do that. Is that better? You the one to ask that? Yeah. Okay, so because we're at half-second intervals, it will take 11 of these things added together to get h of 5.5. Okay, so just forget that h11 thing. All right. Okay, so really what we're embarking on here is integration. Okay, so we're talking about integration. So let's summarize. What is the idea of integration? The idea of integration is that the value of a quantity or an amount of change can be calculated And this is what we've been talking about as the sum total of many little bits of change. And that's what we're talking about, accumulation. So the value of a quantity or an amount of change can be calculated as the sum total of many little bits of change. So let's review in the tax example. The tax due on $58,000 would be what you would get if you plugged 58,000 into the tax function. So that's thinking of input and output, right? Input 58,000, output the amount of tax you pay on that. But we're thinking of that as in a different way now. You can also think of that as the sum of the tax you pay on every single dollar. In this case, since I'm saying 58,000 bits, that would be the tax you pay on every dollar. And we can write that in the summation notation. Okay, similarly, the height of the ball after 6 seconds. Say the height of the ball after 6 seconds, we could think of as h of 6, input, output, right? Put 6 in, it spits out that height. Then we can think about that amount of height as having accumulated in 12 bits every half second. And then we can write that in summation notation. So this is the underlying idea of integration. Anybody have a question? Can I go on to the next screen? Okay, so some rate of change functions. So here's the familiar rocket basketball rate of change function. So here's a new rate of change function. So these are not. And so this graph shows the rates at which a bacteria population changed in bacteria per hour at any number of hours after the first observation. Okay, so these are not our side-by-side graphs. These are both rate graphs from different real-world applications. That's the rate graph from the rocket power basketball, and here's a new rate of change graph for a bacteria example. Okay. So besides the fact that they're totally different contexts, and things like different colors and font size, besides that, what are some differences between these two rate functions? So how many differences can you name between these two rate functions? Take 30 seconds or a minute. Talk with the person next to Okay. Let's hear your ideas. So what's one difference? Volunteer. What's one difference? Yes, sir.
The rate of change of this one.
You said this one is continually changing, as opposed to that one. How does it change? How does the rate of change over there? Like abruptly, right? Like all at once. All of a sudden it's one rate and all of a sudden it's another rate. So here the rate of change is kind of changing gradually at all times. Other differences? What you thought of? Somebody else? Yes, sir. Yeah. So how can this negative? So can you have a negative number of bacteria? What's up with that? So can you have negative bacteria? So here's a point, 0.5. Maybe this is negative 450. So this ordered pair is 0.5 and negative 450. I'm guessing. Okay, just picking it off. So you have negative 450 bacteria? Yes, sir?
It's from the first observation. So what's the first observation of bacteria? So would be decreasing from that first observation.
So he's saying for the first observation, the number of bacteria is decreasing. Yeah, this is rate of change. It's not number of bacteria, right? So the outputs of this y-axis over here is a rate of change. So negative 450 is bacteria per hour. Bacteria per hour. So the number of bacteria is going down, right? It's less. It's less as time goes by, going down. So that's why we can have a negative rate of change. Other differences? Those are two big ones. Yeah.
The intervals on the intervals at which it changes on the left graph are equal,
Okay.
whereas on the right you can see that one curve is not. You can see the other one, so that
Yeah, so on the left graph, you're saying we have equal intervals of time at which we have constant rates. Do we even have intervals at all over here? We don't really have any intervals at all. We just have this continuously changing rate. Okay. How about in terms of being realistic? How are these different? What's that? Yeah. So how do things change? Do they change? Most things, do they change abruptly in rate, or do they gradually change in rate? Yeah. So like you think of anything that moves is going to have a rate of change graph like that. Not like that. Okay. So that was hypothetical for us to learn something, to get set up for what we're about to do. But really, so the tax example is actually a real world example of this, right? That's having these constant rates and then an abrupt change. That's real in the real world because the tax rate abruptly changes when you get to the certain dollar. But in terms of a moving object, this is impossible. And things moving or quantities changing continuously, you're going to have a rate of change more like this. Okay, new questions. So if we want to track the population of bacteria over a given time, and we want to use this accumulation technique that we've learned, okay, what's the obstacle? What's the obstacle? What is preventing us from making this difficult? How can we want to use the accumulation process that we've learned? Somebody new? Yeah. Well, that's no. So I could give that to you. So yeah. Someone new? Yeah.
Knowing the rate of change at any point in time.
What's that?
Knowing the rate of change at any point in time.
Knowing the rate of change at any point in time. Yes, sir.
The rate of change is changing.
Right. And what this technique that we've done is relying upon what? Constant rates of change. Then we can use delta y equals k delta x. We get a small bit of change is the constant rate times delta x. If we don't have constant rate of change, then we can't use that. We can't apply it to this without having constant rates. Okay? So what we can do is we can use our accumulation approach by creating a function that consists entirely of constant rates that altogether pretend to be this function. So we're going to make a rate function kind of like the basketball, but one that's trying to be like this. It's trying to simulate this one, but it's made up of a bunch of constant rates. Okay? So that's how we can solve it. So once we have this pretend function, we can then start talking about the accumulation of bacteria because we can use our technique of summing up bits of change based on constant rate of change. Okay? So let's do it this way. So we need to set some parameters around that. Now, so there's nothing right or wrong about how you do it. This is just one way to approach it. We want to use intervals of 0.3 hours over which the pretend rate is equal to the actual rate at the ending time, the right side of the interval. So first of all, intervals of 0.3. So we're going to go from 0 to 0.3 right there, and then 0.3 to 0.6. Here's how we're going to break up. And we'll just go to 1.5. We'll just stop there, okay? So just go from 0 to 1.5 hours. So in this first interval, we're going to have a constant rate from 0 to 0.3. So we have to decide, is it going to be, is it going to be down here? Is it going to be down here? Is it going to be up here? What about up here at 1,000? Is that a good pretend rate for this? No. What about at 500? No. What about 200? What about negative 600? No, we're trying to pretend to be the rate, which is going here from like 0 to negative 500. So any constant rate kind of in this range could be reasonable. Okay, question.
I don't think it would be realistic, right? Because this graph is saying that he's checking the number of bacteria at every single given moment.
Right.
So you'd have to like count and then immediately
Yeah, you got the right idea. That the rate is it's continually changing. So we're going to make up a new function that has all constant rates. That's trying to be like this one, and we'll use that one instead. That's what we're called the pretend function. Does that make sense? But you're right. We can't do it with this because as soon as a little time goes by, the rate has changed. So you're exactly right. Exactly right. Okay. So the rate of change is kind of in this range from 0 to negative 500. So we need some kind of method to create this constant rate in this interval. So this is one way to do it. We're going to use the actual rate at the ending time or the right side of the interval. So everyone think to themselves, what is the actual rate of change or an approximation for it at the ending time or the right side of the first interval? Think to yourself, what is that value? And they all said negative, so I'm talking about this actual rate right here. So that's going to be the actual rate, about negative 500. We're going to use that value as a constant rate for the whole interval. So we're starting to build our pretend rate function. It's going to start by being negative 500 bacteria per hour immediately, and then constant rate for the first 0.3 hours. Okay, so now look at the next interval. Again, we want to use the actual rate at the right side, or the ending time of the second interval, to be our pretend rate for that whole interval. Everyone think, what constant rate of change will we use? What constant rate of change will we use? Okay, if you said about negative 400, you were right. So here's the actual rate at the right side. We're going to use that rate. Okay, so our first constant rate, we'll call it K1, is negative 500. And then we got K2, negative 400. K3 will be about what? Negative 100. So again, we're always using the actual rate at the right-hand side, or the ending time of the interval. And then we got one more to go here. Oh no, two more to go. What rate should we use in this interval? About
140.
140, 150. So we'll say 150. So that's K4. K4 will be 150. And then in the last interval, 50. Is that pretend rate of change function accurate compared to the original rate of change function? Say it's very accurate or not very accurate? Not very accurate, right? Because, for instance, this first rate, actually the rate is pretty much always greater than, or always less negative than negative 500 in that first, but we're saying it's negative 500 for the whole 0.3 hours. Okay, so it's not very accurate, but it's a start. Okay, it's a start, and we can actually talk about the total change in the bacteria population in this first 1.5 hours. So what amount of change in the bacteria population will we get in the first 0.3 according to our pretend function? How would you calculate that? So if we call this, say this is, so a little amount of accumulation. So let's say in interval 1, we'll say B for bacteria. The change in bacteria amount will be equal to negative 500, our rate, constant rate, times delta X. And in the second 0.3 hours, our pretend rate is negative 400 What's the change in time? So what are we doing? We're saying delta B equals K delta X. Should be very familiar, right? The change in this case, number of bacteria is the constant rate times change in time. And then negative 100 times 0.3. Make sure the numbers are making sense. Then 150 times 0.3. And then 50 times 0.3. So Kaylin wanted to know, how many bacteria are we starting with? That's an important question. So say we were starting with 2,000 bacteria. According to our pretend rate function, how many bacteria would be there after 1.5 hours? Can you think of the process you would use to get that? So now we start with 2,000, and we've got these constant rates. And from those constant rates, we could get these little bits of change of bacteria. How would we get then the total amount after 1.5 hours? Yes, sir?
Wouldn't the K's that you're referring to actually be the change in B, not the K?
What's that?
Wouldn't, like, because you refer to, like, the negative 500 as K1?
Yeah.
Isn't K the constant rate?
Yeah, this is a rate graph. These are rates. The y values on this axis here are rates. Rates of change. So remember, delta y equals K delta X. And so I'm using the rates to calculate little bits of change. So instead, I'm saying delta B equals K delta X. So now, instead of y, we're using B for number of bacteria, total amount of bacteria. So how would we get the number of bacteria after 1.5 hours according to our pretend rate function? We do 2,000, then plus delta B1, whatever this comes, plus delta B2, plus delta B3. We just add up all these little changes and add it to 2,000. Some of those changes will be negative. Some of those changes will be negative. The first three will be negative amounts of change. Then the last two will be positive amounts of change, which we'll just add them all to 2,000. And that will give us an approximated number of bacteria after 1.5 hours. So let's just write it out this way. Delta B I equals 1 to what? Equals approximate. It's an approximate because our rate function is approximate. Number of bacteria at 1.5 hours. Any questions? Yes, sir.
So like the smaller a change in X is, the more accurate
Yes.
you are.
Make your change in X smaller, you get a better pretend rate function. But you pay for it, right? More work, right? So it's the trade-off. Okay, cards.